Good to see everybody here. Hope you're enjoying the talk so far. So, like Varun said, my name is Josh Slocum. I'm a senior software engineer on the data infrastructure team. And so what I'm going to be talking to you all about today is why my team and I decided to make a seemingly bizarre decision to reinvent the wheel and build a database. So how we're going to accomplish that today. So first, I'll give you all some overview on kind of distributed systems in general and why they're difficult. We'll spend some time talking about some practical applications of distributed systems and some common problems in the distributed data storage space. Then we'll talk about Indeed's biggest data set and how these kind of theoretical problems apply to that data set. We'll go over how it's stored and queried and some of the challenges we're facing there. And then finally, what led us to build our own database and what that looks like. So, as many of you may be familiar, there are a ton of readily available distributed databases on the market. Most of these are either open source or available through some cloud provider. So the question I want to focus on for kind of the first part of the talk is why are there so many different distributed databases? So one really important part of the answer to that is that a perfect distributed system is actually impossible. So what do I mean by this? Well, to understand that, first I want to go over the way we typically model computations in a distributed system. So a computation in a distributed system consists of one single program that's distributed across many different processes. And each of these individual processes does not share any state. They're all completely isolated. So the only way they can talk to each other is by communicating via point-to-point messages. So this means if I'm a process in this distributed system and I want to change something in the system, I can't just change a global variable or any global state. I have to individually communicate this change to every other process via an independent message. So what makes this difficult is that in a distributed system, parts can fail at any time. Though there are two kind of main failure types we talk about in practical distributed systems. The first is crash failures, where if I'm a program executing a process, it can die partway through. We also talk about message failures, where both processes, the sending and receiving, are alive, but the message between them either gets dropped or just delayed arbitrarily. So with this kind of theoretical model, we can understand probably the most important theoretical result in the field of distributed systems, which is the FLP impossibility result. So the FLP impossibility result was a paper published by Fisher, Lynch, and Patterson titled The Impossibility of Distributed Consensus with One Faulty Process. So distributed consensus is kind of a fundamental building block of distributed systems. It basically means if we have n processes, we want to get them all to agree on a value that was proposed by one of them. And this is used in many things for transitioning state, to communicating, to making decisions in distributed systems. And what this result said is it's actually impossible. Specifically, it's impossible to guarantee any decision is final in a distributed system if messages can be delayed and processes can crash. So in other words, distributed systems are impossible. Great. So you might think that when this result came out, all of the distributed systems researchers packed their bags and moved on to whatever the next big field was, right? But thankfully, a lot of them decided to take it as a challenge. They were like, well, if there's no perfect system, what can we do? How close to perfect can we actually get? So that's one impossibility result. The other kind of more popular impossibility theorem about distributed systems you might have heard of is the CAP Theorem, which basically says that any distributed system can have at most two out of consistency, availability, and partition tolerance. So consistency is just when every read request receives the most recent data. Availability is that every request receives a non-error response. And partition tolerance is that your system is tolerant to partitions in the network if nodes can't communicate to each other. So this theorem was initially posed as three independent properties, but actually in practical distributed systems, it's not really the case. Most production-grade distributed systems have to tolerate failure and experience them on a regular basis. So really what this says is we need to tolerate partitions, and you can actually characterize crash and network failures as versions of partitions. So really, if we experience a failure, we just have to choose between consistency and availability. That's all this says. So the result of this is we have two separate but powerful theorems in distributed systems that tell us we can't do everything. There can be no perfect distributed system. And on top of the theoretical limitations, there are just many different types of problems that people making distributed systems are trying to solve. So I want to dive a bit more into that and some of the common applications in distributed systems, specifically data storage. So when you're looking at distributed storage technology, kind of the top layer, you've got applications that need to read or write data. And the layer those usually talk to is the record layer, which is something like a database or a file format. And you can think of a record as just like an individual row or element or anything like that. So the key difference between databases and file formats is the databases have a much more complicated and richer API that allow applications to do read and writes of arbitrarily complex data, whereas most file formats are very simple. So to do record-level operations on a file format, you usually need kind of an additional metadata layer or some additional libraries around building that functionality. And then below the record layer, if there's another storage system in this hierarchy, it's usually something really simple like a block storage or a distributed file system. So what I want to focus on today is this record layer, like databases and file formats, because that's the layer applications commonly interact with, and this is where a lot of the interesting kind of trade-offs and problems are. So what are some of the common problems? The first one I want to talk about is partitioning data. So if you're not familiar with the term, data partitioning just means you take a table or a group of records and split it up into two or more smaller subtables or subgroups of records, which are called partitions. So why do we do this? Well, one reason, if your data is too big for one server, you've got to split it up somehow. But another key reason is actually for performance. If we have different subsets of our data that are accessed by different queries, if we actually put them on different servers, we can more efficiently parallelize and isolate our computation. So how do we actually do this? There are two common partitioning schemes that are typically used. The first is called range partitioning. So range partitioning is when you take your primary key or some part of your individual record that's ordered, like a timestamp, an integer, a string, anything that has order to it, and you split your database up or your file system up by ranges of that data. So for example, you could think of a dictionary as being a data set. And if we range partition the dictionary, each chapter is a different range of data. So dictionary is effectively range partitioned by the first letter of a word. So in this simpler example, if we take our colors from the dictionary and range partition them, we'd have two partitions. One is colors that start with B, the other is colors that start with G. So this is actually pretty great for looking up data. For example, if we had the query, find me all words that start with B, I only have to look at one partition, which means it's really efficient to do lookups. But on the other hand, our new data incoming for writes might not be evenly distributed across our partitions. For example, in the English language, the distribution of the first letter in a word is very non-uniform. It's actually 350 times as likely for a word to start with the letter T as the letter X, which means if we're ingesting new data with this pattern, our T partition is going to get way more load than our X partition. We'll have a really imbalanced set of partitions. So the alternative partitioning scheme is called hash partitioning, where you basically take some part of your key as identifier and run it through a hash function. But this data doesn't actually have to be ordered like range partitioning does. And if you're not familiar with hash functions, basically they just mean they're a class of mathematical functions where you take an arbitrary length data and map it to a fixed length data. For example, mapping any possible distribution of data to a fixed number of partitions. So for a dictionary, if we wanted to do something like this, we could, for example, use the number of letters in the word as our hash function. Then on that same example, we'd still have two partitions, but they'd be different. We'd have words with 5 letters in them, and then words with 4 letters in them. And this isn't as good for looking data up, because now if we want to do that query, find all words that start with B, we have to look at multiple partitions. So that's more expensive and basically uses more resources. But most hash functions aren't really the number of letters in a word. Most hash functions are actually uniform, which means that they uniformly map all of your arbitrary length inputs into the fixed length set of inputs. Or in other words, they will evenly distribute our data across our partitions, which guarantees a much more even workload. So in other words, we have yet another aspect of distributed systems where there is no perfect solution. When you're choosing between range and hash partitioning, you effectively have to choose whether to optimize for reads or for writes, which is unfortunate. So as a result of this, many of the kind of active research or common things people are working on is how to improve these partitioning schemes, find new and improved ones, or often find ones that are specific to one application that work really well for that instance. So the second problem I wanted to talk about is updating and deleting data. As you're probably well aware, many data sets have records that are often changing, which is actually a really big problem for file systems, because especially for our large-scale distributed file systems, most of them are actually immutable, or write once. So this means that if I start writing my file, after I'm done writing it, I can't change it. I'm done. So if I want to make an edit to that file, that's kind of unfortunate, because that means I need to make a copy of that file, apply just my edits to it, write that to a different file, and then replace them, which is obviously hugely inefficient. So for example, if I had a 100 gigabyte file and I wanted to take 10 bytes off the end, I'd have to write another 100 gigabyte minus 10 byte file, and then delete the old one and replace it with a new one. So the term for why this is bad is write amplification, which is basically the term for how many bytes on disk you have to change to make a logical change, or more formally, physical I/O divided by logical I/O. So in an ideal case, this is 1. If I want to change a byte, logically, I change it on disk. But obviously, in the case we saw in file systems, this is much larger. If I had to rewrite a 100 gigabyte file to change 10 bytes, I had a write amplification of 10 billion, which means we're doing 10 billion times as much I/O as we could be doing, which is obviously a bad idea. So thankfully, databases do support record-level updates and deletes, but it's still not necessarily free. Whenever you insert, update, or delete a record in a database, you have to update the database index, which is a relatively expensive and high-contention operation. And then on top of that, depending on what database you're using, that database's storage engine might be optimized for different things. So in databases, there are two common types of storage engines that are used. And if you're not familiar, storage engine just refers to the mechanism the database used to actually store data on disk. So the first is a B-tree based storage engines. For example, MySQL's InnoDB uses a B-tree. It's kind of an older storage engine, but the nice part about it is that in the B-tree, every single record has just one place it lives on disk. So this means if I want to go update it, I only have to go one place, which means I have a write amplification of 1, which is basically the best we can do. But the unfortunate part is because every item on disk is in a different location, every item on disk, to update it, requires a random I/O access. And if you're not familiar with the difference, random I/O accesses are much, much more expensive than sequential accesses on, especially spinning disks, because they literally go in a circle, but on pretty much every type of storage medium. So this really limits the throughput in the number of operations per second you can do. So to counteract that, the log-structured merge tree, or LSM-Tree, was developed, which kind of takes the opposite approach. Now, instead of having one place for every item, if I want to update an item in the database, I just add it to the end of a log file. It's really simple. So the benefit of this is now we're doing a bunch of sequential I/O to add new data to the database instead of random I/O, so we can get much, much higher throughput. But the trade-off is that now we got to actually go merge that data together eventually. So we have to flush the data to disk and then do some background combining of the data, which means we end up actually rewriting the data multiple times. Or in other words, we have higher write amplification. So once again, we're faced with a situation where there is no perfect answer. The B-tree-based storage engines will give you guaranteed low write amplification, but it limits your throughput because you do a bunch of random I/O. Whereas log-structured merge trees have higher write amplification, but since all writes are sequential and you can do really efficient sequential reads, it gives you much higher throughput as opposed to the B-tree. Great, so I just dumped a bunch of theory on y'all. So now what I want to do is dive into a practical application of all this theory using Indeed's largest data set. So we'll go through how we store and query it, what it looks like, and what are the challenges we're facing with it are. So you can probably guess that Indeed has a bunch of data, being the #1 job site in the world. We have a ton of traffic, we have a bunch of jobs, we have a bunch of resumes, company ratings and reviews, salary data. You could probably keep guessing, and you'd guess a lot of different data that we have. But none of these are actually our largest data set. So our largest data set is our log repo, or log repository, which is basically a repository of thousands of different types of events that any team at Indeed wants to record and then do some sort of analysis on later. Now, this analysis could be anything that team wants, but some of the main use cases are building machine learning models or analyzing the results of an A/B test to understand what user behavior was like. So a big example of one of the uses of log repo is the Indeed job search site. So as you saw earlier, one of the main functions of Indeed is that people go there to find jobs. So if I'm a job seeker, I go to Indeed.com, type in software engineer in Austin, and hit search. I just generated a log event. So whenever a user does a job search on Indeed, we basically make an event kind of chronicling that search. So this is roughly what that looks like in our log repository. So every log event in our repository has three things. One is a type, in this case job search, that identifies what kind of event this is. The other is a unique ID, or UID, which contains a bunch of uniquely identifying information like when the log happened, where it happened, and other things like that. And then obviously the data the team wants to use in their analysis. So in the case of job search, this would be what that person queried, where they were, stuff like that. So the way we read from log repository is that every query is for a time range of one specific type of events. For example, we could look up job search logs from yesterday, is what this query would be. So now that we've talked about kind of the very high-level view of what log repo stores, I want to go into more about how we actually store it and what the challenges are there. So one of the big factors is we have a ton of this data. We have tens of petabytes of this data, which we partition into buckets of time and type using a partitioning algorithm. And basically, every bucket of time and type is one giant file that's compressed and stored in Hadoop Distributed File System, or HDFS. So one other interesting characteristic is we store a ton of this data per server. We store about 100 terabytes per individual server before compression and replication, and this is across hundreds of servers. So it's a lot of data. So that's what our current log repo has looked like. Obviously, it's worked pretty well for Indeed up to this point, but there are a number of inefficiencies that we need to improve on. So number one, our log system is currently not real time. So when we write these logs, each application writes them to their own time-bucketed file. Then we gather all these time-bucketed files, sync them to one central place, and then upload them to our HDFS cluster. So the nature of this write pipeline means that the time from when an application first records a log to when it's actually readable for consumption is never lower than 30 minutes and is actually often up to a couple hours with decent regularity. So because of this delay, our processes that actually analyze these logs have to run on a time delay and read large amounts at a time. So they take a while, which means that sometimes we can't actually complete our analysis of a deploy or a change in user behavior or anything until the next business day, which is really bad for our velocity, for our ability to make decisions based on data, and basically everything else related to that. So one other big problem is that since we write these files, we're kind of trying to get them into log repo quickly, we initially write them in a smaller, less optimized format, or a smaller bucketed, less optimized format, and we don't combine them into the format more optimized for reading for at least a day. So this means that jobs accessing the most recent day of data are slower, do more I/O, and they're more complicated than we'd like. Usually this is actually the opposite of what you want. Since most of our jobs are analyzing the most recent data, we'd ideally like the most recent data to be faster, not slower. And then one other really, really big problem is that rewrites and deletes are very painful. Because we have these giant immutable files, if we want to remove even one log entry from a file, this means we have to take that 100 gigabyte file, remove 10 bytes, and then write a new one and replace it. So we have a very, very high write amplification, and doing rewrites of our log repository consumes a ton of resources. So these are some pretty big problems. So how do we fix them? Oops, some of my slides went away. But basically the problem is that we have a triple of three things for every row in log repo. We have the type, unique ID, and data. But because the query only involves a type and time range, we can actually construct a key value mapping from type and UID to data. And then we can put this data in a key value store. So basically, instead of a file system, we need to be using a database. Here we go. My slides got backwards. So yeah, since we have three elements of each log repo row, we use these two to construct a sorted key value mapping from type and unique ID to data. So then we can put them in a key value store, which has a really simple API. It's a type of database kind of like a map or a dictionary, if you're familiar with. So we can put stuff in the key value store. We can place one key value pair in there, also known as a write. We can get a value for a key out of the key value store, also known as a random read. And then if we have a sorted key value store, we can find all key value pairs between two keys, also known as a range query or a sequential read. So in other words, if we had log repo in a database with this API, we could fix all of our problems. So number one, instead of writing our logs in this time-bucketed, inefficient fashion, we could instead put them straight in a message queue, like Kafka, for example, which would enable us to decrease our latency from over 30 minutes to potentially under 1 minute, which would be huge. And then since most key value stores, or since every key value store doesn't store the last date of data differently, we'd be a lot more efficient there. But in addition, most key value stores have some form of caching built in. So since most of our consumers are reading the most recent data, we'd actually be doing less I/O for the recent day of data, not more, which is exactly what we want. And then again, since databases actually support record level updates and deletes, rewriting and deleting log repo goes from very complicated and hugely high overhead to super trivial. And the last thing is that one thing we don't currently have is that get function, the ability to get one single value out of log repo for a given key. So because we don't have this currently, it's hard to say what our developers could do if they had this functionality, but I think we're really excited about this as well. So now that we know that it seems like a great idea to move log repo into a database, we need to figure out what a database that's actually capable of storing this data looks like. So number one, we have petabytes of data, so our database needs to be petabyte scale. And number two, all of our queries are for a time range of one type of data, so our database has to support range queries. That's pretty easy, some simple requirements. These are effectively our technical requirements. So if our key value store doesn't do these things, there's no way we can make log repo fit in there. But also as a business, we have some other implicit requirements, mainly time and money. So we have to consider not just the theoretical limitations of our key value store, but also how much it costs. This is how much it costs to deploy and run, how much it costs to find and train people to actually maintain the system and monitor the system, and how much it costs to take our data and consumers and move them from the old system to the new system. So this cost leads us to some additional, not exactly technical requirements, but more of business requirements, like high data density. So as I mentioned earlier, we're able to store a huge amount of data per server, about 100 terabytes of data. And this actually saves us a ton of money because we don't have to buy nearly as many servers to store this data. So if we wanted to switch to a key value store that didn't support this very high level of data density we have, we'd have to throw our current hardware in the trash and buy a bunch more servers, which is not really economically feasible. Also, all our data, as Chris mentioned, is stored on our own hardware on premise. So if we wanted to move to the cloud, we'd have to pay a bunch of money to actually move our data there, and it would be much more expensive to maintain long term. Plus, we already store all of our data in HDFS in the Hadoop ecosystem. All of our consumers are optimized around querying it from Hadoop. We have a ton of operational experience running Hadoop. And basically, it would make a lot of business sense, even though it's not a strict requirement, that our key value store be able to take advantage of the Hadoop ecosystem and integrate seamlessly with our existing systems. So these are our requirements for a key value store. Now we can do our build-buy analysis because we actually know what we're looking for. So I want to walk you through some of the components of how we did that. So there's, as I mentioned, a giant space of potential databases available. So first, we eliminated all databases that don't meet our two technical requirements: petabyte scale and range queries. So then we took a look at our business requirements and only looked at databases that met those. Turns out there aren't any. So to understand why, I want to go through all of our business requirements and show why there aren't any databases that meet these, or just more of that there aren't. So let's just take a look at the ones that meet our hard technical requirements and walk through them one by one. So we need a database that runs on-premise. We want a database that has high data density or where you don't have to worry about it because it's hosted in the cloud. And then we also want a database that takes advantage of the Hadoop ecosystem. So as you can see, we're not even close. There are no databases out there that both support high data density and are ones we can actually run on our own hardware. Additionally, almost none of these databases integrate well with the Hadoop ecosystem. So in other words, if we want a database to put log repo in, we have to build one ourselves. So that's what we did. We made a new database and we called it Osiris. So the short version, maybe the one-sentence version of what Osiris is it's a hash-sharded distributed key value store that runs on top of Hadoop. And we built Osiris to store both log repo and many of our other NoSQL data sets. So a bit more implementation details just to get that out of the way. We use HDFS to store data. We use Zookeeper to handle metadata and do coordination between servers. The Osiris daemon itself is written in Java because the whole Hadoop ecosystem is all Java-based. And we use Thrift to enable clients to make remote procedure calls to Osiris. So despite the fact that we as a group just went through this whole analysis of what our requirements are and what our cost is, we still get a bunch of questions about why we built Osiris. People were like, wow, it seems crazy that you built your own database. Or, that sounds really hard. Why'd you build your own database? Why didn't you just use blank? Whatever your favorite NoSQL database is. So unfortunately, we don't have time to go over a lot of these. It'd actually be interesting to. So the one I want to focus on is probably the most common version of this question we get asked, which is, why don't you just use HBase? And that's because on the surface, it's actually a relatively reasonable question. So if you're not familiar with HBase, it's the columnar key value store that comes with most distributions of Hadoop. And if you are, you probably already noticed that it meets two of our requirements. HBase was actually designed around having efficient range queries, and it stores data on Hadoop, and we can run it on our own hardware. But the reason we can't use HBase for log repo is because it does not scale nearly enough. So what I want to focus most of the rest of the talk on is understanding this specific point, why HBase doesn't scale, what scaling means, and how we built Osiris to actually overcome the limitations HBase has. So when we talk about database scaling, there's two main types we talk about. One is horizontal scaling, which means you're able to take your data and your database and distribute them across a large number of servers. The other is vertical scaling, or scale up, which means you're able to store and query a huge amount of data per server. This also enables high data density. So really for log repo, if we have 100 terabytes of data per server across hundreds of servers, we need both of these things in our database. And unfortunately for HBase, it can't do either. So now I'm going to focus on these specific two aspects, horizontal and vertical scaling, understanding what HBase couldn't do that Osiris can. So I want to focus mainly today on horizontal scaling, or scaling out. So part of the requirements for scaling out a database of this size is we need to actually distribute our data evenly across the cluster. And also once we do that, we ideally want to distribute accesses to it evenly as well, so we're actually taking advantage of all the resources we have. Then another requirement is when you have a database that scales to hundreds of thousands of machines, machines are just going to die, and you're also going to need to expand your cluster relatively often. So whatever database we use needs to be able to support efficiently adding or removing machines with relatively low overhead. So when we consider partitioning data or distributing data in a key value store, the easiest way to think about it is to think about assigning each key to a server. So how do we do that? Well, one of the most common approaches is called sharding, where basically it's a form of partitioning where you assign each key to a shard and each shard to a server. So the nice parts about sharding is that it kind of has this independent assignment that you can handle separately, but also it gives you the concept of key locality, which basically means that if I have keys that are stored together in the same shard that are close in my key range, my batch writes and range queries will be more efficient because they have to go fewer places to find that data. So in an ideal key to shard assignment, we want our keys to be evenly distributed among shards, and we also want to get some key locality for keys close together in the key range. So the way HBase does this is through a method called dynamic range partitioning, which is a bit of a mouthful. Basically, we talked about range partitioning already. So HBase breaks up the key range by range of keys and assigns one shard to each disjoint key range. So the dynamic part means that as shards grow, if one gets too large, it'll actually split it down the middle of the key range for that shard to form two new shards. So this means that HBase basically ends up mapping the distribution of keys in your dataset to its shard distribution, which is actually really cool and works well for a lot of datasets. But it has one really, really big problem that prevents it from scaling horizontally, which is hotspotting. So hotspotting is basically just when the distribution of keys you're accessing isn't the same as the distribution of keys in your dataset. So obviously we talked a bit about hotspotting earlier, where we had uneven distributions of data in English. But probably the most common practical version of hotspotting, we see it indeed, is when you have data where new data incoming is always at one end of your key space. So one common example of this is time series data, because new timestamps are always larger than everything that came before it. Another common example is if you have an integer valued key, and you keep increasing it, maybe like an auto increment ID or something, that's always going to have the newest data at one end of your key space. And what this does to HBase is because it breaks data up by range, only one shard is handling all of your new writes, while the others aren't doing anything. So in other words, you have one server in your cluster that's completely on fire, while no other servers are doing anything, they're all idle. Right, so we're not really scaling horizontally because we're not actually using all of our hardware. We're not distributing our requests evenly. So if we rephrase the initial comparison between hash and range partitioning in these kind of new terms specific to sharding and HBase, we can tell that range partitioning is prone to hotspotting because it breaks data up by range, but it has great key locality. On the other hand, hash partitioning doesn't have hotspotting, but it doesn't really have key locality either. So what we realized when we were making Osiris was that it doesn't have to be entirely one or entirely the other. What if we actually had a spectrum from no hotspotting and no key locality to a bunch of hotspotting but great key locality? Then you could kind of get a best of both worlds, where I have enough key locality that my queries are efficient, but not so much key locality that I run into major hotspotting issues. And the other insight we received was that databases like HBase, for example, kind of bake this choice into the database. In HBase, you get range partitioning, you're stuck with hotspotting. But in Osiris, what we realized was we could actually design a sharding scheme that's flexible enough that each individual user could pick for their table how much hotspotting and locality they wanted. So that's what we did. So the way Osiris handles sharding is that we use hash partitioning to do the initial key to shard assignment to help prevent hotspotting, but we let the user determine how their key gets hashed. One other thing we learned from HBase is that instead of forcing partitioning on top of it like you have to do sometimes, Osiris is aware of the internal hashing scheme so that it can store and query the data more efficiently. So the method we actually use to do this is that in Osiris you have one logical key, but Osiris actually makes you break your key up or split it into two parts, a hash key and a sort key. So the hash key is the part of the key Osiris will run through the hash function to determine where your shard lives. But it doesn't actually add that to your key or modify it in any way. This means that within your shard, Osiris can sort data on your original key. And the way Osiris sorts data is actually sorts first on hash key and then on sort key. You can kind of think of your key as a tuple of those or a concatenation of those. But what this does is it allows us to get all the benefits HBase has of actually having your data sorted within a shard, but with hash partitioning on top of that to help avoid hotspotting. So because all data with the same hash key will get run through the same hash function, all data with the same hash key will always have the same output of the hash function, so it'll always get stored on the same shard. And then because within a shard, we're sorting data on hash key, what you're essentially doing with your hash key is Osiris is forcing all data with the same hash key to have good locality. So that's kind of the key insight here, is that when you pick your hash key, you are forcing all data with that hash key to be stored together on the same shard. So you're forcing locality and hotspotting for that data, which lets you choose how much locality and hotspotting you want. So to walk through a more practical example, let's say your key is a timestamp, which as we talked about is very prone to hotspotting. So the algorithm, when you construct your Osiris client, you have to tell it how to split your key into a hash and a sort key. Key splitting algorithm is what we call it. So for integer value keys, what we typically use is you take a bucket size, let's call it m, and you make your hash key k divided by m and your sort key k modulo m. So what you're essentially doing is grouping your keys into buckets of locality of size m. So for example, our hash key here would be our original key. Let's say we made our bucket size 1,000. Our hash key would be our original key divided by 1,000, and our sort key would be our original key modulo 1,000. So what you can see is that when you stick these back together in the sort order Osiris uses, it's the exact same as your original key, but you've added this user-defined semantic information about how much locality you want in your data set. So to walk you through how a couple different choices of hash key give you different hotspotting and locality properties, let's say your timestamp is like accurate to the second. So if I made the entire timestamp go in my hash key, I would have no hotspotting because every second of data would live on a different shard, but I'd have no locality either. Then if I increased my bucket size to 1 minute of data, I'd have a bit of hotspotting, but more locality. So for 1 minute, all writes would go to one shard, but then they'd switch shards after a minute. And then on ranges of 1 minute of data, both the start and end key can differ by at most 1 or 2 buckets, so we only need to go to 1 or 2 shards to actually read that data, so we have good locality for that time range of query. And then if you increase your bucket size even more, you have more hotspotting, but more locality. For example, for an hour, you'd have an hour of hotspotting, where for an hour, all writes would go to one shard, but you'd have better locality on larger queries. So if you can tolerate an hour of writes going to one shard, that's great, but if not, you need to use a lower bucket size. So this is how we overcame some of the horizontal scaling limitations of HBase. By allowing you, the user, to split your key into 2 parts, the hash key and the sort key. You're good. By allowing you to split your key into a hash key and a sort key, we have this user-defined trade-off for how much hotspotting and locality you want for your specific data set that's independent of the actual database. And the other nice part is because we have hash partitioning built in, you get easy horizontal scaling and guaranteed even distribution of your data and requests among shards. So that was horizontal scaling. I want to spend a bit of time talking about vertical scaling, or scale up. So to start, let's understand why HBase can't scale up. There are actually 2 main limitations that combine to prevent HBase from scaling, kind of inherent in its architecture. So I've taken this quote and the quote after this from the official documentation for the version of HBase we run at Indeed. And it says that the maximum region size, or shard size, is like 10 to 20 gigabytes, and 5 to 10 is optimal. And secondly, that the number of shards per server that's recommended is 20 to 200, mostly because of memory constraints. So we have a recommended range on data per shard and a recommended range on shards per server. So if we multiply these together, we can actually get the recommended range of data density that HBase supports. So you see, if we do that, we get 100 gigabytes per server to 4 terabytes per server. And actually, this kind of affirms what we've seen at Indeed. On our HBase cluster that we were running, we started hitting scaling and stability problems around 100 gigabytes, a couple hundred gigabytes of data per server. So obviously, this is not going to work for LogRepo because we need 100 terabytes of data per server. We need 1,000 times as much data per server, which means even if HBase didn't have hotspotting issues, we would have to buy 1,000 times as many servers. Good luck pitching that to your boss, right? So obviously that's not going to work, so we needed to do something better in Osiris. So what we realized was we need to vastly increase the amount of data we can store per server, but we don't want to sacrifice in performance or any of the other things we need to get there. So this means we either need to maintain the same performance while either increasing the number of shards we can support on one server or increasing the size that individual shards can grow to without performance issues. So actually, one of the useful things we learned from HBase was that each shard inherently has some amount of overhead, both in terms of memory for data structures and buffering, also in terms of coordination costs. The more shards you have, the more complicated distributing them across the cluster is. So we decided to focus on increasing the size of each individual shard. This seemed like a much more straightforward path. So unfortunately, we don't actually have time to go into how we did this, but the really short version is that we did it. So Osiris shards can grow to... I'm happy to talk about this offline as well. We just didn't have time in the talk. So Osiris shards can grow upwards of 10 terabytes per individual shard without running into performance issues, whereas HBase can't really get past 10 gigabytes. So after this theory on how Osiris is supposed to work, you probably want to see how it actually works in practice. So I figured the best way to do that would be to show you what happened when we actually took our biggest HBase table and moved it to Osiris. And this table was our job archive, which, as the name suggests, contains an archive of jobs. Basically, every job that's ever been on Indeed.com is in this data store. So this data set, as you could probably figure, is one of our largest, both in terms of data, but especially in terms of volume of queries. Indeed is a job site, so a lot of our analytics and other stuff makes really heavy use of job data. So this is a super read-heavy data set. So the format of this data is that whenever we aggregate a new job on Indeed, we auto-increment an ID in a MySQL database. So the job ID is just an increasing integer. And the value in this key value store is just all the data we have for that job. So like I mentioned, this data set's very read-heavy. We have hundreds of times as many reads as writes in this database. And it's also has a heavy bias towards recent jobs, specifically ones that are still live on Indeed.com. Those are queried much more frequently. So like I said, this data set was an HBase, and it turns out that HBase's storage engine essentially has a trade-off where you have to increase write amplification to get better read performance. So we actually ended up having to rewrite the entire HBase table every single day in order to achieve consistent read performance, which is basically unbounded write amplification, which is awful. In addition, we were running into hotspotting in HBase, so we had to use a hash salting technique where basically you force hash partitioning on top of the client, which destroys all the benefits of range partitioning that you get in order to handle hotspotting. So it seemed like a great candidate to move to Osiris, because we'll have lower write amplification, our shards can get much larger, and we won't have hotspotting. So we did this, and it turns out it was working great. Performance was better, resource usage was better, people in Slack seemed happier, but it was hard to say that the improvements we were getting were definitively because of the fundamental differences between HBase and Osiris, or just because our big data cluster is super busy as a result of being a heavily used shared resource. So what we realized was that because this data set's so read heavy, we could get reasonably representative and much more precise performance results if we took a read-only version of this data, moved it to an empty cluster, and ran some performance tests there. So that's what we did. So I'll share those results with you now. So in this test, we took our whole job archive and moved it to this other cluster, and we had 4 different versions of our job archive. 2 were in HBase, and the first one is just kind of the normal HBase format that's optimized for writing, and the second one was the one where we rewrote it every day to optimize it for reading. And then we had 2 Osiris versions, one with kind of comparable shard size to HBase, and then one with much bigger shards. So this first row shows the shard size used in each test. So you can see that the Osiris shards in the large Osiris shard test are much larger than HBase's. So the first actual performance test we ran was the random read latency test, or basically, how long does it take to get one value out of the key value store for a given key? So what we'd expect is that the read optimized HBase would be faster than the write optimized HBase, and that's what we see. It's about twice as fast. What we can also see is that Osiris is faster for both use cases, and encouragingly, it's actually even faster for our large shards. So this means we can grow our shards to very large sizes without hitting random read performance issues. So the second test we did was a small range scan. We read a couple thousand consecutive job IDs, which is like 10 megabytes of data. And since HBase had this hash partitioning forced on top on the client side, we actually had to take each range query and break it up into a ton of small ones and then re-merge them all together because we were trying to avoid hotspotting. So this meant that the queries were slower and actually used way more cluster resources to perform one individual query. Whereas in Osiris, because we are able to get that trade-off, we used a bucket size of around 1,000 in our job archive, which means that for small range queries of a couple thousand jobs, we get great locality. We only have to look at a couple shards, so our latency is much lower. And the final test we did was throughput of a full shard scan measured in terms of rows per second. So what we can see here is that HBase is pretty much the same between both results as is Osiris, but Osiris is a little slower. But actually, we think now that this difference is not due to a fundamental difference between HBase and Osiris. We actually think it's due to the choice of compression algorithm used, so we need to rerun this test at some point to see how it holds up. But even if this is still the case, what we can see is that Osiris is pretty much comparable in all main read tests, despite having much larger shards. So because we have comparable read performance, and we can have much larger shards, this means that we can grow our data size per server to much larger values while maintaining the same read performance, which was kind of the whole point. So we did it. Yay. So in conclusion, at Indeed, we have built Osiris, which is a flexible, scalable, and fast key value store. So besides that, we built a pretty cool database, what I hope you learn and remember from this talk is that distributed systems are actually hard. In fact, they're impossible. But not just that practical distributed systems are even harder. In addition to all the theoretical limitations of the systems we're trying to use and build, we have to consider things like cost, like API, like how hard it is to deploy, what the support is, all these other things that make finding the right distributed system actually a really, really difficult problem. So I want to spend a bit of time talking about where Osiris is going in the future, because we just spent the whole talk talking about where it is now. So number one, we are planning to open source Osiris. Thank you. Yeah, we're really excited. We don't have an exact timeline set for it yet, but we are starting some of the work, and we hope that we could get done as early as the end of next year if things go well. So some of the things that by that point we'll hope you'll be able to take advantage of we're adding cloud support, specifically S3 support for Osiris, because Indeed is moving to more of a hybrid cloud model in the future, and we want it to be on the forefront of that. So we now have the ability to store data directly in S3, and actually even the ability to query it out of S3 without going through Osiris as part of the Osiris offering. So that'll be really useful for many people, we think, especially us. One other thing is we want to actually replace HDFS entirely for our production user-facing workloads, because while HDFS is great for analytic workloads, its availability and some of its latency characteristics make it suboptimal for directly user-facing traffic. We also have a scheme to improve the storage engine even further than we already have, which will allow us to decrease write amplification by an order of 10 while keeping the same random read performance. So we'll be even more efficient at what we're doing already. So thanks so much for taking the time to listen. I really appreciate it. Thank you. Yeah.